Hey everyone, welcome back, and today let's solve Leetcode problem 3403 titled Find the Lexicographically Largest String from the Box. So we're given a string word and an integer num friends, and Alice is organizing a game for her num friends' friends. And there are multiple rounds in this game, where in each round the word is split into num friends non-empty strings, such that no previous round has had the exact same split. And all these split words are then put into a box, and we need to find the lexicographically largest string from the box after all the rounds are finished, right? And just to kind of quickly define what lexicographically largest means, it says a string A is lexicographically smaller than a string B if, in the first position where the two strings differ, string A has a letter that appears earlier in the alphabet than the corresponding letter in B. If the first of the minimum of the length of A and the length of B characters do not differ, then the shorter string is the lexicographically smaller one. Right, and effectively, we need to find the lexicographically largest string from the box after we complete all of these rounds, right? So looking at how this pans out in the examples here, in example 1, we have our word to be DBCA, 4 different characters, and we have 2 different friends, right? In this case, our output would be DBC. That is the largest possible lexicographic-wise string of characters that we can get that would be stored in the box. And the reason why is because all the different possible splits that we can make would be D and BCA, right? We basically just make a split here at this D, and we have BCA. Then we split DB, right? So then we'd have D, and then we'd have this BC, rather we'd have this DB, and then we'd have CA. Or we split it as DBC, and then just the singular A at the end, right? And if we take all those different splits, the largest possible one lexicographically that would be stored in that box would be DBC, and that's why we'd return that, right? In example 2, we have our input string word to be GGGG. We have 4 different friends, and in this case, really, we only have one possible split. Why? Because we have 4 different characters and 4 different friends. We'd split each time. We'd have one G, another G, another G, another G, or G and then G and then G and then G. And so really it's just G as your output as the lexicographically largest possible and the only possible result in the box. So for the constraints here, we see that the length of our input string word is going to be between 1 and 5 times 10 to the third power. It's rather large, and word is only going to consist of lowercase English letters, and the number of friends we have is also always going to be guaranteed to be between 1 and the number of words that we have, right, quite palpably, which brings us to the main observations that we really need to make to solve this problem, right? And the main one is really that lexicographically largest substrings, they're often going to start at positions where their suffix is the largest, right? And basically, we really just have to consider those different suffix-based approaches or properties in our input string word, if you will. Right, so how do we solve this problem? Using that main suffix kind of strategy here, effectively we'd find the lexicographically largest suffix of our string and then just determine the maximum allowed length for any substring, and the way we can actually calculate that would just be length of word minus num friends plus 1, so we're allowed to make that many splits for all the different friends, so they at least each get a character, right? And we simply just extract that prefix of the largest suffix up until that maximum allowed length to maximize the number of characters that we get for that suffix, right? So we consider the most significant substring without actually exhaustively generating all of the possible splits and making it less efficient doing that method, right? So with that, let's go ahead and get into the solution here. Now before I even start, just to quickly have a very, very quick edge or base case here, if we only have not one friend, meaning num friends is equal to 1, immediately we just return the word. Why? Because we don't really need to make a split. The entire word is going to be the only possible substring, right? And so in that case, we just return however many characters we have in that same order because we only have one friend, right? We can't really do anything. The only possible substring that we could even have would be the entire word itself. Now, here is where we actually find that lexicographically largest suffix here. And the way we can do that is I'll call S basically an object, if you will, of a last substring helper method that I'm going to define. And technically, this isn't actually allowed in Python if I define objects of classes before I actually define the classes in the editor. And so I'm going to adjust that once I actually finish kind of this explanation, right? So effectively, this helper function last substring is going to find the lexicographically largest suffix of the input string word. And we're really just storing that in this, integer, or rather variable s. Now then we have to actually from there calculate the maximum length that we're kind of allowed to make splits up until, and again that formula would be sz is what I'll call that. It's going to be the length of the input string word minus the number of friends, and then we'll have to add one for that to account for that offset here. Basically, it's going to be the maximum length that any substring can have, ensuring that we don't actually exceed those constraints of the length of or the number of characters that we have. So each friend gets at least one character, right? When we actually, make those splits for the number of friends we have. Now, we have to then actually return our appropriate substring. And the way we do that is to return s starting, or rather up until the minimum of the length of s, or sz. Right? So basically it'd be from the starting of the input string s up until the minimum of either the length of input string s or whatever value sz is, right? And recall, basically that's just sz is nothing but the maximum length that we can have, right? For all the splits, for all the different number of friends we have. And basically that's just returning the prefix in this case of the largest suffix up until the allowed length. Now, that's basically it for that kind of pre-computing here. Now we have to actually start, to define that last substring helper method, right? And so I'm going to define it right now. I'll call it last substring. And for my parameters, I'm really just going to take in one parameter. That's just going to be, you guess it, an input string s. And in this case, we're going to eventually pass in word for it, but that's all it's going to take, right? I'll just call it s, right? It's going to basically find the lexicographically largest suffix in s, right? Now, we're going to be doing something called the pointer method, if you will, or using pointers to help find this lexicographically largest suffix. And I'll be using 3 different pointers, I, j, and k. Initially, they're each going to be set to 0, 1, and 0, respectively, right? I and j are going to be used to compare our suffixes, and k is just going to be used as an offset of those 2 pointers, right? And now, here's actually where we start iterating through the string. In this case, since we have pointers, we're going to iterate over it using a while loop here. So the way our while loop condition would work is while j plus k, while the sum of those 2 pointers is still less than the length of our input string s, meaning it's still in bounds, we'd always just first check if s at I plus k, if that's equal to s at j plus k, we know immediately we can just increment k by 1. Now, if, or rather else if, s at I plus k, if it's less than s at j plus k, rather than being equal to it, well then we'd set I, rather update I, to be the maximum of I plus k, sorry, I plus k plus 1 rather, to account for that offset, or simply just j. And once we update I, we then update j to then be I plus 1, and then set k back to 0 for that resetting of the offset. Now, for the else condition here, if neither of those conditions are true, we'd simply just update j to be j plus k plus 1, and then reset our offset k to be 0. Now, how does this while loop really work here? Just to kind of quickly reiterate what it really means. Effectively, we're always comparing in each iteration of this while loop the characters at the positions I plus k and j plus k. And again, I and j are our suffix comparisons, or comparison pointers, if you will. K is just our offset, right? Now, if the values at those, or characters at those indices, are equal, we then increment k, which is our offset. However, if the character at I plus k is less than the character at j plus k, we'd have to move I to j, and then update our offset accordingly to again be 0 once we actually move them back, or we just move j forward, and then again straightforwardly update our offset k to be 0 again once we move them to each other. Right, and effectively, finally, once we actually finish this while loop in this helper method itself, we'd return s up until, or rather starting from I, index I, that is, up until the end of the array. Basically, s starting from index I up until the end of the array would basically just be the lexicographically largest suffix, while still also keeping that property of, not making too many splits where we have an invalid, according to an invalid number of friends integer. Right now, again, since Python doesn't like if we have objects before we define classes, I'll take this section of the code and I'll just transfer it down below underneath once I actually define the last substring, right? But the logic still remains the exact same, right? So unless I made any syntax 0, 0, there should be accepted and there should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So again, on a high level, how are we really solving this problem? Effectively, really, we're just focusing on that lexicographically largest suffix, and we're avoiding the need to actually generate all those possible substrings. That's why the solution is, that much more efficient, right? And effectively, really just using, pointer techniques and string comparison techniques, using them without actually having to make any unnecessary computations in our helper method itself, right? That's why the solution is the most efficient according to just generating all the different possible splits, which would be rather much less efficient, right? We're just finding that lexicographically largest suffix, we're then determining the maximum length and extracting the prefix of that largest suffix up until the maximum length that we're allowed to do, right? So for the runtime complexity of this solution, overall, at the end of the day, it's really still just linear or big O of n. Why? Because that last substring function would run a linear time relative to the length of word, because it really just is a one-pass solution, so technically with the different pointers. And out for our memory or space complexity, it's actually going to be constant or big O of 1. We're not actually using any direct auxiliary memory or any extra data structures, if you will. If you've noticed, we're really just using some extra integers, but they don't actually scale linearly with the input size, and so we are using a constant amount of extra space, only a few integers, right, which makes your memory or space complexity big O of 1. So if you guys enjoyed the solution, I learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.